In exploring the boundary between neutron stars and black holes, we wonder if there is an unknown intermediate form lurking between the two. Here, we introduce the concept of quark stars, which is regarded as a strange bridge between neutron stars and black holes. According to the mainstream theory of stellar evolution, after a massive star undergoes a supernova explosion at the end of its life, two types of dense objects usually form, neutron stars or black holes. Specifically, slightly more massive stars may evolve into neutron stars, while more massive ones may collapse into black holes. But a new study by scientists suggests that between neutron stars and black holes, there may also be an intermediate form of objects, quark stars, a discovery that further broadens our understanding of the universe's extreme physical phenomena. Scientists speculate that adding matter to a quark star may prompt it to collapse further and eventually evolve into a black hole. Quarks, one of the fundamental building blocks of matter, reveal the key to understanding macroscopic phenomena in the microscopic world. The atom, the basic unit of matter, consists of a nucleus with electrons moving around it, while the nucleus harbors protons and neutrons inside. Delving further, quarks are thought to be the elementary particles that make up protons and neutrons, marking another fine level in the exploration of the structure of matter. It was previously thought that at the end stage of a star's life, after experiencing a supernova outburst, the extreme pressures within it due to collapse would compress matter to very small scales. During this process, electrons within the atom are forced into the nucleus, causing the nucleus to break up and combine with protons to transform into neutrons. At this point, a neutron merger pressure is generated, and this force is effective in counteracting the high internal pressure generated by the collapse. If this force is strong enough to stabilize the situation, the object will evolve into a neutron star. On the contrary, if the neutron merger pressure is unable to resist the force of the collapse, the neutrons will be further compressed to the limit, and the object will eventually collapse into a black hole. However, modern science has concluded that since neutrons are made up of quarks, there should be another type of object made up of quarks after the neutron star, which is a quark star. If the star is more massive, then the neutrons may first be compressed into its own constituents, the quarks. Instead of just crushing the neutrons to pieces, like a black hole. Scientists have been studying quark stars for decades, but still haven't confirmed them. In other words, quarks are still a hypothetical star. And the reason why we can't make any more breakthroughs in the study of quarks is because of a few unanswered questions about quarks. First of all, quark theory suggests that quarks are trapped inside protons and neutrons, and that there are no separate quarks. So if quarks can't exist on their own, how do quark stars form? Given that quark theory has been correct in many predictions, there's very little opposition to quark theory. So for scientists to prove the existence of quark stars, they may have to prove that quarks can exist on their own. There are also new research theories suggest that the so-called neutron stars may be the quark stars that scientists are struggling to find. Why? Because these scientists believe that neutron stars may well have the ability to further crush particles themselves. The pressure at the core of a neutron star can reach a terrifying 10 to the power of 28 atmospheres, which is 30 quintillion times stronger than the pressure at the center of the Earth, and 300 quadrillion times stronger than the pressure at the center of the Sun. The neutrons inside it have probably undergone further splitting into exotic matter under the heavy pressure, and could this exotic matter be a quark soup made up of quarks? In the 1980s, American physicist Edward Witten even suggested that strange quarks might be more stable than iron nuclei. If this hypothesis is valid, it would mean that quark stars would be more stable than neutron stars, and that the universe might be populated with brand new objects made of exotic quark matter, quark stars. Quark stars are also capable of generating relativistic jets of particles in the region of their magnetic poles and radiating electromagnetic waves, exhibiting the characteristics of pulsars. This begs the question of whether quark stars are included in existing observations of neutron stars. Unfortunately, the complex and variable interactions between quarks are still an area of theoretical physics that is difficult to fully navigate. As a result, the existence of quark stars and the exact state of matter inside them are still shrouded in mystery. However, if the existence of quark stars can be confirmed through astronomical observations, It will undoubtedly provide us with a key page to unravel the nature of pulsars, and at the same time promote a deeper understanding of the interactions between quarks and the nature of exotic quark matter. In the face of this challenge, scientists are working to find the key clues that distinguish neutron stars from quark stars. Current research focuses on three: the mass-radius relation, the rotation period, and the radiation properties. With respect to the mass-radius relation in particular, neutron stars and quark stars exhibit very different patterns of behavior. Neutron stars, as gravitationally bound systems, follow a specific pattern between their mass and radius, while quark stars, due to the intervention of strong interactions between quarks, show very different mass-radius curves, which provide us with valuable clues to identify these two types of objects. Unfortunately, based on current observational data, most of the pulsars fit the expectations of both neutron stars and quark stars in terms of their mass and radius relationships, making this feature ambiguous and difficult to clearly distinguish. Nevertheless, one suspected object named SAX J1808.4-3658 has attracted attention, but its exact location is not yet known. In addition to the mass-radius relation, the rotation period has become another focus of exploration. As a gravitationally bound object, the rotation speed of a neutron star is limited by the centrifugal force of the surface matter, and calculations have shown that its rotation period must not be less than about 1 millisecond to maintain stability. In contrast, small-mass quark stars, whose stability relies more on interactions between quarks, are able to support higher rotation speeds, with theoretical rotation periods as short as 0.1 milliseconds. Unfortunately, however, even sub-millisecond pulsars rotating at such high speeds are difficult to detect directly with current technological means. Turning to the radiation properties, the surface of a neutron star consists of atomic nuclei and electrons, thus producing atomic spectral lines. Quark stars, on the other hand, are composed entirely of quarks and do not produce atomic spectral lines, but may exhibit thermal radiation characteristics similar to metal surfaces. This inference is encouraging to astrophysicists because there have been no conclusive observations confirming the existence of atomic spectral lines in pulsars, and instead there are pulsars that exhibit good blackbody radiation properties. In summary, although there is observational evidence in favor of the possibility of quark stars, none of this evidence is conclusive, leaving the question of whether a pulsar is purely a neutron star, a quark star, or a hybrid of the two still open. At the same time, no conclusive method has been found to effectively verify whether a pulsar is a quark star. Currently, it is widely recognized in the academic community that short rotation periods are a strong clue to identifying quark stars, so the discovery of a sub-millisecond pulsar would greatly enhance the credibility of the existence of quark stars. Thankfully, the Fast Radio Telescope, located in Guizhou, China, has already significantly enhanced humanity's ability to search for pulsars with its superior observational capabilities. People are full of expectations, believing that if sub-millisecond pulsars really exist, FAST will be able to capture them and provide key clues to solve the mystery of the nature of pulsars.